very excited to speak with you this evening. Thank you to Martin and Cress for extending the invitation. So the title here, I kept it a little bit broader, Industrial Heat and Decarbonization Solutions. I work for a company, Energeticsin, and lead our industrial decarbonization analysis and modeling team at the company. So I'll give a quick introduction of the company. We're a clean energy consulting firm, I should probably start the timer, that has been in business for almost 50 years. We were actually formed at the same time as the Department of Energy was formed in the late 1970s. Our founding fathers recognized that this fledgling thing called the Department of Energy would really need contractor support to further its agenda. So over the near 50-year history of our company, we've developed four main support areas: transportation, manufacturing, which is where I reside, green buildings, and energy and resilience planning. Some of the work that we do, we're a company with a really deep technical bench. We really focus on technology, techno-economic analysis, and do technology feasibility studies, really trying to understand the benefits associated with technology deployment within a given industry. We'll back that up with market and economic assessments. We're a company that is brought in to do third-party evaluation. So if there is a major player that's doing a technology demonstration, a first-of-its-kind deployment of some nascent pathway, we'll be an impartial third party that's brought in to validate those assumptions that are made. We do a lot of strategic planning and technical road mapping, so we are contracted by our clients to do stakeholder engagement. We'll bring in stakeholders in a given industry, pick their brain. We do all the meeting planning. We facilitate those meetings, do all the data analysis and the reporting associated with those stakeholder engagement events. Given that we have a deep technical bench, you need to do two things as a scientist or engineer. You need to be able to talk, you need to be able to write. So we do writing and graphics for our clients. Equally important to technology development is the legislative, regulatory, and policy framework associated with it. What can and cannot be done. So we evaluate those opportunities. And then finally, maybe you're an agency and you want to prop up a new program. We will come in and design a program for you. We will do active project management and run your peer reviews and your merit reviews. We have really exploded in the last 3 years. Since the Bipartisan Infrastructure Law and the Inflation Reduction Act were passed, I think we've doubled in size. We're now well over 100 staff, and we're located all across the country. Our headquarters is in Columbia, Maryland, which is about 35 miles northeast of D.C. We have an office in D.C. right across the street from the Forstall building, which is the headquarters of the Department of Energy. We have an office in Clinton, New York, for our support of New York clients. Southern California, in San Diego. We have an office in the Pacific Northwest, in Washington, and also right here in Colorado. So this talk today, I'm going to give a quick introduction of myself, and then launch into the talk where I'll cover challenges of industrial heat decarbonization, and then I'll get into, well, what are the opportunities? What are the solution pathways to decarbonize industrial heat? I'll then kind of drill a little bit deeper into the history and the particular pathways associated with thermal energy storage or thermal batteries, and then give some specific information about thermal batteries and some of their competing technologies. So a little brief blurb about myself. I hail from the great state of Indiana, and studied chemistry and German at Indiana University. And I liked those two things so much, I decided to go to Germany and study chemistry in Germany. So I did a master's degree at the Clausthal University of Technology, and afterwards worked as a researcher at the German Aerospace Center for networked energy systems. My girlfriend at the time told me I better come home or else. So I came home and we got married and everything was great. But I came back here and went to the Colorado School of Mines to do my PhD in applied chemistry, materials chemistry to be specific, but leveraged a lot of those relationships in Germany to continue the collaborations with Max Planck Institutes for colloids and interfaces and coal research. I then did a postdoc in material science at NREL, where I actually did research in thermal energy storage, so I'll touch on that a little bit. And now in recent years, I've transitioned to consulting, and I'm now a senior scientist and lead our industrial decarbonization analysis and modeling. So let's start talking about the industrial sector. Building a net zero clean future must include decarbonization of the industrial sector. The industrial sector accounts for 33% of the nation's primary energy use and 30% of its CO2 energy-related CO2 emissions. And we anticipate our economy to grow from now until 2050. And the anticipated growth of 30% in the industrial sector could contribute to a 17% increase in CO2 emissions. So we really need to focus on industrial decarbonization and really consider it an opportunity for America's economy. The manufacturing sector contributes nearly $2.8 trillion to the US economy, generates 12% of our GDP, and supports over 11 million jobs in this country. And it's critical to decrease CO2 emissions while maintaining global competitiveness of US manufacturing. So this horizontal bar chart is millions of metric tons of CO2 released annually in the United States. And you see up at the top, chemicals, refining, major industries in this country. The dark blue are manufacturing sectors. The light blue are non-manufacturing industrial sectors of construction, agriculture, and mining. All are part of the parent industrial sector. And all of these sectors, whether it's chemicals all the way down to glass manufacturing or fabricated metals, are extremely different and heterogeneous in their processes. And so it's important that we work across all industrial subsectors to decrease overall emissions. And it's clear that there is no one-size-fits-all solution. This donut chart on the left shows on-site energy use, so the energy that is used inside the manufacturing facilities in this country, of all industrial sectors. And what you see is that over 50% of the on-site energy use is for process heating, simply combusting fossil fuels to generate heat to drive some sort of industrial process. On the right are bar charts that show the distribution of process heat of the five energy and emissions intensive industries in this country: chemicals, refining, food and beverage, iron and steel, and cement. And from left to right, you see the process heat demand for particular sectors. So sectors like food have very low process heat demands, less than 80 degrees Celsius, mostly for drying and dewatering of food. But if you go all the way to the right, process heat demands greater than 1,000 degrees Celsius, industries like cement and iron and steel. What's clear is that the solutions for those two options are completely different. I want to emphasize that a little bit further. Thermal demand below, let's say, 150 Celsius is a really excellent candidate temperature regime for electrified technologies. Heat pumps are a term, a technology that people are throwing around a lot now. But you can't just throw heat pumps into a cement kiln or a blast furnace in an iron and steel manufacturing facility. So thermal demands above 150 Celsius may require alternative sources of heat. This is a stacked bar chart that shows the on-site combustion emissions in dark blue, off-site emissions. So the purchase of electricity from merchant electricity for a food manufacturer, for example. The light blue is on-site combustion emissions, and the orange is process emissions, so emissions that are simply evolved out of a chemical process. Cement comes to mind, transitioning from calcium carbonate to calcium oxide to make cement, right? CO2 is released in that. That's a process emission. We can't do anything about it. Chemicals, big dog on the left. All of our energy and emissions intensive industries are on the left. And we could invest trillions of dollars just decarbonizing those 5 on the left. But I want to emphasize by this that there is a long tail of industrial sector emissions. We could focus on those 5 that are in the green box, but collectively on the right, all those that are not inside the green box, while individually they don't have a major footprint, collectively they're still a major emissions contributor. So I want to emphasize here that we need to innovate core thermal operations for cross-sectoral impacts. Focusing all of our efforts on chemicals may not be suitable for foundries and textiles all the way on the right. But this cross-sectoral approach is challenging. It's challenging, but it's necessary. In the text here, I say thermal processes and systems are essential and pervasive in industry, and every major industrial subsector needs heat and uses heat, but in different ways. So like I said in the beginning, there may be paper or food operations that are simply for drying and require low process heat, less than 100 degrees C. But as you get up to distillation processes in the chemicals industry, melting and forming operations for the plastics industry, smelting for metals, or calcination in the cement industry, you start getting to process heat demands that are very, very high. But we really have had a shot in the arm through the Inflation Reduction Act and the Bipartisan Infrastructure Law, an unprecedented amount of investment. This report from the Office of Policy estimates that the IRA and the BIL together represent a historic investment of more than $430 billion toward modernizing the American energy system. Never been done before. And while that sounds like a lot of money, and it is, there are still systemic barriers to industrial decarbonization. A separate report published by the Department of Energy just this past summer estimates that the investment needed to decarbonize just the 8 industrial sectors that are in those little icons on the bottom could cost somewhere between $700 billion and $1.1 trillion. That far exceeds what we have from IRA and bill. That same report estimates that 60% of CO2 reductions by 2030 will come from technologies that do not yet have a net positive lever with existing IRA tax credits, which means that 60% chunk is going to require research and development into technologies that have not yet been industrialized. So I want to emphasize here that targeted investment for research, development, and pilot-scale demonstrations is needed and is an opportunity for U.S. manufacturing. But the U.S. Department of Energy has a real guiding light in the Industrial Decarbonization Roadmap, which was published in support of efforts from my company in the fall of 2022. And this outlines barriers to industrial decarbonization and opportunities for industrial decarbonization. In that report are highlighted 4 interrelated and cross-cutting strategies to pursue in parallel. They're called the industrial decarbonization pillars, and they are energy efficiency, industrial electrification, low-carbon fuels, feedstocks, and energy sources, and carbon capture, utilization, and storage. Together, these things, working in tandem, can decarbonize the industrial sector. As a part of that analysis, there were deep dives into 5 specific energy and emissions intensive industries: iron and steel, chemicals, food and beverage, refining, and cement. And I want to highlight here on this landscape chart the technology pathways that were identified. The colors indicate the 4 separate pillars and the technologies that are necessary from our baseline year of the early 2020s to our target year of reaching net zero by 2050. And in this landscape chart, you start to recognize that industrial decarbonization is going to require approaches on multiple levels. So you have to start thinking about innovating at the core fundamental unit operation level. So instead of producing iron by throwing iron oxide into a blast furnace and throwing petroleum or throwing carbon, also called coke, at it to reduce it, we need to think about using clean hydrogen to reduce iron. We need to think about using hydrogen instead of natural gas to produce process heat. But it goes beyond just the core unit operations. We need to start thinking about, well, how am I going to get hydrogen into my facility? You know, am I going to start producing hydrogen on site? Do I have the footprint to produce hydrogen on site? Am I going to buy it from some off-site merchant? How much is that going to cost me? Where am I going to get it from? What's the carbon intensity of that hydrogen? If I'm using gray hydrogen produced with natural gas, what's the point of investing in hydrogen, right? I'll just use natural gas. But it goes beyond the facility level. What about beyond the plant bounds? And this is where I highlight energy and thermal energy storage and recovery. That if we really want to realize decarbonization on an economy-wide scale, we need to be thinking about all these things in tandem. Innovating on the core fundamental unit operation level, innovating at the facility level, innovating on the economy level. And so this starts bringing up some questions. What are the implications of expanded hydrogen use and generation? What are the implications of new thermal energy sources and systems? How can we do this smart? You know, not 1860 industrial revolution, but how do we do this smart in the 21st century? How do we integrate automation? How do we integrate all these things together? How do we do data analytics? How can we leverage that? What does transition to clean electricity really look like in an industrial facility? And how can we leverage our analysis and our know-how to continue pushing policy forward? IRA and bill are great starts, but we need to keep moving forward. But I want to emphasize that there's hope. This is kind of the flagship graphic from the Industrial Decarbonization Roadmap. If you guys want to read all 480 pages, I really encourage it. It'll put you to bed. But if you take nothing else away, take something away from this. If you look at the far right, the stacked bar chart there of the different colors, that is the most optimistic near net zero scenario analysis that we did. And it shows that if you do these 4 decarbonization pillars in tandem, carbon capture, utilization, and storage, low carbon fuels, feedstocks, and energy sources, electrification, energy efficiency, by 2050, we could approach nearly 90% emissions reductions. But that remaining 10 on the bottom there, alternate approaches, shows that even if everything goes swimmingly, there's still research, development, demonstration that's going to be needed to innovate emerging nascent technologies to fill that gap. And the roadmap highlights specific recommendations that really guide the investments that the Department of Energy is making today. We need to continue to advance early stage RD&D, research, development, and demonstration. We need to invest in multiple process strategies. We need to really emphasize demonstrations. Like, industry is averse to risk. They want people to show them that there's no risk. Let's demonstrate that there's little to minimal risk so that these technologies can be industrialized and incorporated into the commercial sector. We need to address process heating. I hope I've emphasized that. That's the big dog that we need to tackle. We need to decarbonize electricity sources, conduct modeling and systems analysis, and engage with the community and develop the workforce that is going to take us to those 2050 goals. So I gave you an overview now on industrial decarbonization. And now I want to drill a little bit deeper and start picking at industrial heat a little bit more specifically. So the Biden administration, one of the first things they did is they kicked off this initiative called the Energy Earth Shot, which harkens back to the moonshot that Kennedy kicked off in the 1960s, that decarbonization is such a critical need that we need an all-hands-on-deck approach to tackle some of these really critical cross-cutting challenges. So I encourage folks to look up the Energy Earth Shots. There's 8 of them in total. There's one on long-duration energy storage. There's one on hydrogen, on geothermal. There's one on buildings. This one, my favorite, of course, is the Industrial Heat Shot, which has a target to develop cost-competitive industrial heat decarbonization technologies with at least 85% lower greenhouse gas emissions by 2035. That 2035 is really important because we need to meet this goal so that we can really meet the overall 2050 goal, right, 15 years later. So in this heat shot, the imperatives of decarbonization of U.S. industrial heat were identified. The first is that incremental solutions are insufficient. Business as usual is insufficient. We need to have another industrial revolution that reinvents the manufacturing and industrial sector. CO2 emissions from inefficient material flows are a problem. We need to be efficient in production processes, and greenhouse gases are just one environmental factor. What about pollution more broadly? What about people that are affected at the fence line? What about historically disadvantaged communities? We need to make sure that the next generation of manufacturing is sustainable and does not add additional burden to communities that have historically shouldered much of the burden of manufacturing. Cancer Alley in the Gulf Coast comes to mind. The Industrial Heat Shot identified some key characteristics. Manufacturing is diverse, it's heterogeneous, it's got a lot of different processes, it's got a lot of different operations. Heat is used in tons of different ways. So we need solutions that meet or exceed operational demands today, that are cost competitive, industry's got to buy into this, and can achieve industrial scale, really important. So the source on the bottom here, the Industrial Heat Shot Summit, happened October of last year, just a few months ago. The Secretary of Energy presented, Deputy Secretary Turk presented, John Podesta from the White House, congressmen were there presenting on the importance of this industrial heat shot. And in that summit, 3 pathways were identified. Pathway number 1, we need to generate heat from clean electricity. So this includes, heat pumps, thermal energy storage is thrown in there. We need to also innovate clean heat from alternate sources. So can we leverage the sun to generate heat? What about nuclear? What about using the heat that's right beneath our feet in the geothermal resources? Hydrogen, sustainable fuels. And the final pathway is really a game changer. Can we develop innovative, low or no heat process technologies? Could we just rethink this all together? Could we just find a way to not use heat and make the same stuff that we use every day? So underneath all of this, underpinning all of this, is that we need to develop technologies that span all of this. We need to do things like energy storage and advanced materials and everything that serve as the foundation for these pathways. So I really want to focus on that pathway number 1, generating clean heat from clean electricity. Reducing emissions by electrifying equipment, using clean heat, improving energy efficiency. Examples are heat pump, microwave heating, resistive heating, thermal energy storage. The opportunity here, a lot of words, really sorry about that, is, we got to reduce fossil fuel use. Given specific applications, the economics, the geography is really important. The cost of electricity is way different in Washington State than it is in North Dakota. I'll touch on that a little bit later. What are the advantages of this pathway? Well, we can be more efficient in how we deliver heat. We can reduce heating time because electrical heat is more efficient than combustion heat. We can improve temperature uniformity, improve quality of products, the yield of products. Boy, that really gets industry people excited. We can reduce cost, also makes industry people really excited, and waste byproducts. But there's key technical challenges. Achieving these temperatures is challenging, and especially given specific application requirements. Scale. We got to get these things to industrial scale. And cost. The cost is a challenge because the cost of electricity relative to natural gas is a major barrier in this country. I mentioned Washington and North Dakota. Washington has really, really cheap electricity prices, largely because of their hydroelectric production. So they are only 3 to 1, the cost of electricity relative to natural gas. Cost of electricity is 3 times more expensive than the cost of natural gas in Washington state. Whereas in North Dakota, where they have very limited access to low-cost electricity production, it's more like 5 to 1. How do you make those economics work out on an industrial scale? So now it's time for the obligatory duck curve. If you guys have ever come to CREST meetings or listened to renewable energy talks, you got to look at a duck curve sometime in the presentation. So here it is. And what this shows is the difference in electricity demand and the amount of available renewables throughout the day. So when the sun is shining, solar floods the market, wind floods the market, and drops off demand. But then as solar comes off, the sun goes down, people start coming home, they turn on their lights, their washing machines, they kick on their ACs. We really ramp up our electricity demand, right? Everyone has hopefully seen the obligatory duck curve, which shows capacity across hours in the day. We have a lot of renewable resource during the middle of the day, very little renewable resource at the end of the day. So what this shows, and this graph shows 2012 through 2020, just 2020. And already in 2020, we started reaching a point where we were at risk of overgeneration. We're producing more electricity than we could possibly need at 12 p.m. in the afternoon. But then when everyone comes home and starts turning on all their devices, boy, that puts utilities in a really difficult position with this rapid ramp up in demand. And the result is something called curtailments, that we have all of these renewable assets deployed, wind farms and solar farms. And what's happening is we're reaching a point where we're producing so much that we're having to shut off those assets. We're having to curtail clean electricity production because we have too much of it on the grid. So this is data from California, published by the government's very own Energy Information Agency, EIA. And it shows monthly curtailments in the state of California from 2015 up until the present day in 2023. And what you see is this nearly exponential rise in monthly curtailments in the state of California because there's so much renewable energy generation in that state. Well, let's think about this on a monthly scale. On the right, what you see are curtailments in the months of the year. And the big issue is right around now, as we're entering into the spring. Sun starts coming out a little bit more, but it's not too hot. Our ACs aren't kicking on as much, and so we're generating a lot of electricity. We're overproducing a lot of electricity in a seasonal fashion. Too much in the spring, not enough in the summer. And so, energy storage is a solution to this. Can we capture the overproduction that we have when we generate it, and then use it or dispatch it when we need it? So, likely a lot of you have seen a chart like this that shows the energy storage capacity, so how much can be dispatched, so kilowatt hours on the y-axis versus the capacity, how much you got on the x-axis. And what is on here is a bunch of different energy storage technologies. And as is typical, lithium-ion batteries are kind of closer to the bottom left. You can turn them on right away, but they don't have a whole lot of capacity. We all know we got to charge our phones like every night because it runs out of batteries, right? Whereas things like thermal energy storage are near the upper right. They have a lot of capacity. They can discharge over a long period of time, hours, maybe even days. And I'm just trying to highlight here, and I want to emphasize here, that I'm not saying thermal energy storage is better than lithium-ion batteries. We need all these technologies here. We can't quickly ramp up a thermal energy storage facility. It's like a diesel engine. It takes a while to warm up, but then it just chugs along. Whereas lithium-ion batteries, I need power right now, boom, I got it. So these things need to be working in tandem to give us a holistic approach to energy storage. So let's start talking about thermal energy storage. I'm at 30 minutes. Hopefully I'm not boring you guys. Thermal energy storage applications have really taken root in three main end-use applications. The first is industry. This makes sense. There's really hard to decarbonize sectors. I hope I've demonstrated that with really high process heat demands. Thermal energy storage will enable and ensure that a manufacturing facility can have reliable 24/7 heat delivered to their operations. And it allows them to load shift, right? That's the big thing with energy storage, right? Overproduction during the day, electricity is really cheap. Can I pull that off the grid and use it during those high ramp times when electricity prices start skyrocketing? The second, and this is, I think, where a lot of the learning for thermal energy storage has come from traditionally, is the power sector. Thermal energy storage has been used in the power sector to make power production dispatchable, using it when I need it. The third application I won't touch on in this talk. It's district heating. It's commonly done in Europe, less so in the United States. So let me give a little bit of history. I'm kind of a thermal energy storage traditionalist. As Martin said, I used to be at NREL. I worked in concentrating solar power thermal energy storage. And as I said, since the 1990s, thermal energy storage has really come from power production. So let me kind of just give an overview of what thermal energy storage is for those that have not come across this in the past. So thermal energy storage has really come in lockstep with the development of concentrating solar power. Concentrating solar power is sort of the redhead stepchild of photovoltaics. Everyone knows solar power means PV, right? Solar panels on our houses. Well, the other solar power is concentrating solar power. So let's talk about that a little bit. In principle, what you have is a bunch of mirrors that reflect the sun's rays to a focal point. In this case, it's a tower. And in that tower, what you can do is start flowing a heat transfer fluid around. And in that focal point, the heat transfer fluid will start heating up. Isn't that great? And then you can take that heat transfer fluid down, and you can store it in some tanks. You can store heat in a vessel, and then whenever the market says, boy, I need electricity right about now, you can flow it out of your tanks. I don't think I have a pointer, so I'm just going to use my hands. You can flow it out of those tanks to a power block. And then it's really no different in principle to a standard, utility, natural gas, or coal-fired power plant. You got a heat exchanger where you exchange the heat in your heat transfer fluid with a working fluid, usually steam, and then it flows through a Rankine steam cycle, spins a turbine, which goes to a generator. You generate electricity, boom, you got power. Isn't that great? And this is a technology that has been deployed somewhat successfully in the United States. This is a bird's eye view of Crescent Dunes Solar Energy Project in Tonopah, Nevada. It's a molten nitrate salt power tower configuration similar to the schematic I showed on the previous slide. Molten nitrate salts is the heat transfer fluid and the storage medium at this facility. It has 2 tanks, so you see that in the foreground there, 2-tank thermal energy storage. It's rated to have a storage length of 10 hours, and it had a capacity, at least they claim to have a capacity of 110 megawatt electric. Pretty substantial. This is a cautionary tale, though. This particular project received about a $740 million grant from the DOE Loan Program Office to build it. It was built and commissioned in 2014. It started production in 2015 and almost immediately started experiencing problems. This company has since gone bankrupt. It's changed hands a bunch. They fixed the problem, but it doesn't nearly have the power production that it was rated to have when the project was conceived. The issue is right there in the foreground, the thermal energy storage system. The tanks started experiencing leaks. And boy, you don't want to have molten salt leaking all over the place. It causes a lot of problems. So, you know, there's still a lot of learnings. I could talk all day about Crescent Dunes, but I just want to emphasize that this is a technology that can be built at scale, and we can take the learnings and the pitfalls from certain issues from projects and apply that to new industries like the industrial sector. So let's talk about thermal energy storage pathways. What options do I have if I'm a manufacturer and I wanna install thermal energy storage in my facility? Well, there's three main kind of technology pathways available to you. You have sensible heat energy storage. That means your thermal energy storage medium does not change phase. It stays solid or it stays liquid. And the main materials that are used, that are deployed commercially, are molten salts. I showed that on the previous slide. This has been something that's been demonstrated since the 1990s. And increasingly what's becoming popular with newer startups and successful young companies is solid media. Can I use solid particles? Can I use refractory ceramic bricks like the bricks right here? These suckers have a lot of heat capacity. You could put a bunch of heat in that and you could heat them up to 1,000 degrees C and they ain't gonna go anywhere. The other pathway is latent heat thermal energy storage. So what this means is storing heat. Uh-oh, we lost it. It'll come back. Here we go. How long has that been going on? Have I just been talking to no one? Okay, cool. All right, awesome. An engaged crowd. I really appreciate it. Latent heat thermal energy storage. So what this means is storing heat in the form of a phase transition. So typically transitioning from a liquid to a solid and back and forth. So this could be salts. This could be metal alloys. The final one is thermochemical energy storage. So this is really storing heat in the form of chemical bonds. So you can think of metal oxides, ammonia, like real chemicals like ammonia and hydrogen. So I'll do a quick overview, kind of pros and cons of each of these. Let's start with sensible heat storage. Again, there's two main pathways there, liquids and solids. So for liquids, like I said, this has been demonstrated. It's been successfully demonstrated. Molten nitrate salts, as I showed on a couple slides, have been in the works since the Solar 2 project was done at Sandia National Labs down in New Mexico in the mid-1990s. The benefit of liquids is heat transfer is really well understood. We do heat transfer in industry all the time. That's no big deal. Big issues here are salt material stability. I mean, think about water. It can boil, it can break down, it can change phase. It's really funky. Same thing with these media. Corrosion issues are really, really tough. High temperature, very acidic salts will just eat away at a tank and cause it to leak, for example, in Tonopah, Nevada at Crescent Dunes. And then salt freezing. Imagine at Crescent Dunes they have tens, if not hundreds of thousands of tons of salt. What happens if that stuff freezes? The freeze point is about 400 Celsius. If it goes below 400 Celsius and you've got a block of salt, it's not melting again. Real big concern. Solid pathway, if you start thinking about using bricks instead, well, that mitigates a lot of the concerns that I just referenced for the liquid pathway, right? It's not going to break down. It's not going to corrode. It's not going to freeze on you. It's a solid. But heat transfer is a bit more of a challenge for solids. The transport of the solid can be challenging if applicable, if you're using sand or particles, which are very popular right now. You got to move that around somehow. See if it comes back on me. And the final thing, I'll just talk, is instead of corrosion, we have erosion, right? That will start rubbing, it's back, and cause mechanical degradation of your system. On this slide, I just kind of lumped together latent heat and thermochemical energy storage because they're less cool than sensible heat storage. Latent heat, it's attractive because it's more energy dense. If you're transitioning from a solid to a liquid, you can store more energy in a phase transition than you can just in a single phase of matter, whether it be a solid or a liquid. So with increased energy density, that means I don't have to have as big of a footprint. That's attractive for industry. And the thing is, we have centuries of experience of this. I mean, how much have we dealt with the water, liquid water, and ice transition? In Berlin, downtown Berlin, I was just there in the summer, they have a big tank for water, and they do thermal energy storage there with the transition from water to ice. And that's great, but the problem is that you can't reach high temperatures that are really needed for industry. It's pretty good for like district heating, and I'm going to heat up my water heater at home for my personal use, but not for high temperature applications. And material degradation is a problem as well. For thermochemical, this is really the only way that we could ever possibly achieve seasonal energy storage. I want to use solar energy from the spring and dispatch it in the winter. The only way to do that is to really store energy in the form of chemical bonds. It has high energy density as well, but it also has material degradation issues. So I've given a little bit of a history of thermal energy storage. So what is a thermal battery specifically? Well, can I just take away the solar receiver from a concentrating solar power plant, and can I switch that sort of energy input to something else, like, for example, abundant, clean electricity from the grid during periods of overproduction, like I was mentioning earlier? And then, if you think about that, if you sort of conceive that, it's not too different from a concentrating solar power plant. It's just that your thermal input is a little bit different. So instead of the sun and a solar receiver, you just have electricity that is driving some sort of heat pump, or an electric heater or something, that then goes into a thermal energy storage system that can then be discharged to a heat engine, like a Rankine steam cycle, like I showed before. And it's established on very sound thermodynamic principles. It's great. And it really enables you to do a lot of things. I've mentioned concentrating solar. I shouldn't talk about it anymore. But thermal energy storage allows you to get over intermittent renewables. I hope I've demonstrated that in this talk. It allows you to take base load operations like nuclear. Nuclear produces this amount of electricity all the time, and it doesn't change. If it does change, we have problems, right? So it allows you to take firm electricity production and make it dispatchable, right? Use it when I need it. It allows you to capture high-quality unused heat. That's particularly interesting for industry, right? There's a lot of waste heat in industry that just gets vented out the stacks. We could capture that with a thermal energy storage device. And solar chemistry as well. And what you get out of this is dispatchable power. I'm going to get power when I need it. It allows you to load shift, sometimes seasonally, but certainly on a kind of diurnal basis, tens of hours kind of thing. It allows you to deliver high-quality process heat to whatever. For me, industry. It allows you to do a lot of municipal operations, like water purification for our drinking, and other kind of applications for low-quality process heat. And it allows you to do thermal chemistry. Can I make the products that we all rely on using inputs other than fossil fuels? So I just want to highlight at the end of my talk here some resources. This is data from a publication that came out over the summer. DOE put out a pathways to commercial liftoff for long duration energy storage. So again, this is focused kind of on power production, not on thermal energy storage for industry, but it's instructive because it looks at the barriers, opportunities, and economics of competing energy storage technologies, including thermal. So on this chart, you see the capacity, so how much energy you got in your thermal energy energy storage device versus its duration of discharge. So how much energy can I get over an X amount of time? And in the red box is where thermal energy storage, right there in the middle, is where thermal energy storage sits. Yeah, it'll come back. Again, a lot of the things that I've been talking about are indicated on this slide. Chemicals, storing energy in the form of chemical bonds will give you seasonal energy storage for as long as you want. Whereas things like batteries and flywheels are sort of on that lower capacity, lower discharge duration on the bottom left. Something really instructive about this is the report looked at a lot of the properties or aspects you want to see out of competing energy storage technologies. So I think I drew a little box around thermal there. It's one of those technologies that can give you multi-hour, maybe multi-day energy storage capability. And on this chart, they looked at how many hours can you store? What is the levelized cost of storage? So how many dollars per megawatt does it cost me? What's its size? How much can I deploy in megawatts? What is its average round-trip efficiency? That's what RTE stands for. And TRL. TRL is technology readiness level. 9 means this thing is ready for prime time. It's ready to be deployed in industry. 1 means this is still in the academic phase, needs a lot of research and development. And what I want to emphasize here, last thing I'll say is dark blue means really more desirable. Light blue means less desirable. And anyway, point is, thermal energy storage has a lot of desirable attributes. It's dark blue, really great, except for the levelized cost of storage is on the light blue end. So there's still a lot of work to make this technology cost competitive. And then the final sort of eye-crossing chart that I'll show today is a lot of the supply chain vulnerabilities. We need to be thinking about this from a Department of Energy standpoint. We can't be reliant on foreign supply chains or materials from conflict zones or from political adversaries. These are things that we need to consider in the Department of Energy. And we have certainly seen the issues with supply chain reliance as a part of the COVID-19 pandemic. So it's really important to study this. And here we have a stoplight approach. Green, yellow, red means low, medium, and high risk. Gray means there's no apparent risk for raw materials, acquisition, the subcomponents necessary to build your system, the manufacturing and assembly of your energy storage system, and the workforce needed to build it. So highlighted here is thermal energy storage. And I really want to emphasize on the sensible heat at the very top, which is what is being deployed commercially today, and I think will be the front runners from now until 2050. It's all gray. That there are no apparent supply chain risks for this particular technology pathway. So it really demonstrates that this is something that we can invest in with some level of certainty. So kind of wrapping things up, I just want to emphasize that industrial decarbonization is informed by stakeholder engagement and by analysis. It is really important that investment decisions, whether you're the Department of Energy or you're a business, that investment decisions are made in a defensible and justifiable manner. And so we have done, on behalf of the Department of Energy, stakeholder engagement for thermal process intensification, talking with experts in the field. We've written the industrial decarbonization roadmap. There are commercial liftoff reports for industrial decarbonization and for energy storage. And we've done deep dives into specific technology pathways in the quadrennial technology review. And across DOE, industrial decarbonization is really getting a lot of attention. This is kind of a map of DOE. And across the 4 pillars that I mentioned before, feedstocks, energy efficiency, electrification, there's a 5th pillar of manufacturing technology innovation now. But all these offices are participating in industrial decarbonization technology development, whether it be foundational science by the Office of Science, the applied energy offices that really focus on R&D and first of its kind demonstration and deployment, and then the new offices that have been propped up by the Inflation Reduction Act. The Office of Clean Energy Demonstration is brand new and really focuses on large-scale demonstration. The Office of Manufacturing Energy Supply Chains, MESC, brand new, focuses on deployment of technologies at commercial scale. Oh, and I just want to emphasize this, I made it big. Industrial decarbonization is getting so much attention, the DOE has made a landing page for all industrial decarbonization technologies, agnostic of any one office here or there. So one-stop shop for all of your interests in industrial decarb. And finally, this was a slide I just put in at 3:15 because the DOE, and in particular my client, the Industrial Efficiency and Decarbonization Office, announced $254 million to decarbonize the industrial sector across 49 projects. And super high tech, I took a screenshot of 2 projects I really want to highlight. This is part of the flexible industrial energy use topic, where 2 projects were funded, each of them getting $5 million of federal funding to decarbonize or to develop technology associated with those 2 hot topics I mentioned: sensible heat storage for the liquid pathway and the solid pathway. The top one is a company, Electrified Thermal Solutions, that is developing electrically conductive fire bricks, so like really fancy bricks, that will store heat and dispatch it for industrial use. The second one that I'm particularly excited about because of my background in chemicals and refining, is through Shell, an oil refiner that is going to be deploying molten salt technology that has been commercialized or demonstrated and commercialized since the 1990s in their manufacturing facilities to produce decarbonized steam. So very exciting there. So stay tuned over the next several years as these projects progress. And with that, I thank you for your attention, and I'm happy to take questions. How bad was I? 52 minutes. Sorry about that.
Okay, and I have the microphone for the Q&A. First question here from Steve.
Thank you, Martin. Thank you. That was wonderful. I appreciate the progress that came through legislation earlier in the current administration. Is there any legislation in the preceding administration that helped facilitate all of this? Enough said.
Well, I mean, in fairness, it's one of those things where you have to talk about things in different ways. And so the Trump administration really focused on a concept called process intensification, which is in principle, can I do more with less? And one of the things that came out of the Trump administration that, in fairness, has been very successful is something called the RAPID Institute, which is an institute focused on process intensification. And I can say just a couple months ago, it was renewed. It was kicked off in the Trump administration and was so successful that it was renewed with another, $70 million for another 5 years. So, yes, of course. Legislation-wise, no. I mean, laws like IRA and bill are really a driving force that levels the playing field for all of industry, right? Dow Chemical is not going to go broke decarbonizing their operations if a competitor like BASF is not going to do it, right? So we need to have strong governmental policies in place that level the playing field for all so that we can achieve our goals, whatever those goals may be. So nothing compares to IRA and bill. They're unprecedented, but yeah.
Okay, Dave.
Thank you. Sam, this was a terrifically interesting presentation, and you did a great job. This is very interesting stuff that I don't think we've seen at a CREST meeting. Those of us in this room have long advocated solar electricity, solar heat. Mm-hmm. There has been residential solar heat through flat plate collectors, evacuated tubes, et cetera, et cetera. Yeah. We've seen that drop off dramatically in residential applications. And it looked to me, correct me if I'm wrong, that most of the pathways that you showed were through electricity. Mm-hmm. And so I'm wondering if any of the current initiatives are taking advantage of the traditional direct capture of heat through the tubes or through flat plate collectors for regular process heat as opposed to the over 150 C.
So yes, there are investments, especially in steam production, right? And for low temperature steam production, I can think of a couple of examples. My intention, by the way, just for transparency, is not really to name company names because I don't want to claim that I'm endorsing any one technology or company. But there are innovators out there that are investing in kind of more industrialized tube collectors that you're describing for steam production for industrial processes. I can think of three actually. One of them's in Italy for pasta manufacturing. Yeah, great, right? For a tomato facility for taking the skins off of tomatoes with steam, and for poultry manufacturing facilities. But no, those are just straight steam. So straight process heat coming from a collector, similar to what you're describing. In a residential application, though, the reason why we're seeing those tube collectors and things really drop off is that the cost is simply not competitive with heat pumps, with PVs coupled with electrified equipment like heat pumps. It's not competitive.
If I may interject one question myself, since you have these connections to Germany, mm-hmm. my own country, mm-hmm. I'd be curious to learn what the European Union or the Asia Pacific Circle does on that scene.
Me too. Yeah. Me too. In fact, that's I'm personally a proponent of increasing engagement across the globe, and kind of I do that in my consulting role as much as I can, rather than being so U.S. centric, to really engage with other people that are driving the decarbonization narrative, like in Europe, like in Asia Pacific. The challenges are so very, very different, though. Mostly because of the cost of energy. Money drives everything, right? And the cost of energy in Europe and in Asia is much higher than in the United States, which really makes the return on investment for decarbonization or energy efficiency measures much more advantageous than in the United States. Approaches are very different. Hydrogen is one of them. Europe is really pursuing aggressively a hydrogen pipeline network, which in the continental lower 48 United States is really hard to conceive because we're such a big country and our metropolitan centers are so spread out. So it's something that I'm personally very interested in, because we have the same overall goal to decarbonize, yet some different challenges.
You mentioned hydrogen in various elements of your presentation. I wondered if you could talk about geologic hydrogen as one possibility.
Geologic storage?
No, geologically produced hydrogen.
I don't think I can. Geologically produced hydrogen, I quite frankly have not come across that very much.
Yeah, I'm not surprised. It's a really recent development, and since oil and gas exploration is still going on at quite an alarming pace, I would say, they recently discovered that there's quite a bit of geologic hydrogen that could be tapped into and then used directly rather than through electrolysis and such. But it is a very new development.
Okay, I'll add some comments on that. I mean, one of the main one priority within the Hydrogen Fuel Cell and Technologies Office within DOE is hydrogen storage and how we can make that economical. I talked about the energy earthshots. The very first earthshot that was ever introduced was the hydrogen shot, which has a goal to produce 1 kilogram of hydrogen for $1 within 1 decade. And 1 kilogram of hydrogen, $1 per kilogram, translates to $7.46 per million BTU. To compare that, natural gas is about $4 per million BTU. So, great. We can produce hydrogen fairly cheaply, almost comparable with natural gas, but that's just production. How do I store, how do I transport that hydrogen to its end use, whatever that may be, a hydrogen filling station in California or an industrial application? So one of the things that that HFTO, the Hydrogen Fuel Cell and Technologies Office, is investigating is underground storage of hydrogen. And one of the only ways that they can do it at scale is leveraging underground salt caverns, because it acts as like a ceramic and it keeps the hydrogen in there. Otherwise, hydrogen, smallest molecule in the universe, likes to leak out of everything. So underground hydrogen in underground facilities, whether, I guess, produced, I'm not aware of it, but or whether it's stored, requires very specific conditions that are geographically specific. There's not salt caverns everywhere in the country.
So one thing I was really grateful for in your presentation was it was a reality check. Mm-hmm. It showed me how incredibly complex and diverse the problem sets are that we're faced with, areas or industries I had never even considered. So I'm grateful for that, because as most of us, I live in somewhat of a media bubble, and I'm constantly bombarded by hopeful messages from new discoveries, and this is going to solve X. But that might be true. It might solve X, but the alphabet has many letters.
It does.
It might not solve Y or R or S.
I hope I didn't come across as too pessimistic or doom and gloom, but it does. Industrial decarbonization of the economy, whatever, is going to require a suite of solutions.
Yes. Are there any innovative technologies that apply to the developing world?
To the developing world? Yeah, that's a really good question. That is a really good question. It's difficult to. I was just at a seminar at Mines back in November where they talked about decarbonization in an equitable fashion. Boy, it's challenging, because obviously, well, the industrialized world is really driving this decarbonization narrative. And we get a lot of pushback from developing nations that are trying to achieve the quality of living that we have achieved in this country and in other countries in the Western world. And they kind of balk at some of the comments or objectives of the Biden administration, because they say, hey, you guys tore up the world in the 1860s. Why can't we do it now? Like, why, what's with this double standard? And so we need to make sure that the United States positions itself as an exporter of know-how, that we take on the risk of de-risking some of these technologies and commercializing these technologies, so that it is more approachable to people in the developing world. Just say that.
Hi. You had mentioned that Berlin, the district heating, using the latent heat storage, and that it's more popular or used in Europe, but not so much in the US. Do you know the reasons why it's not as prevalent here?
I would assume, I've come across a lot of this in sort of like YouTube rabbit holes I'll go into of like companies that are doing cool stuff in Denmark and whatever. I gotta believe it has to do partially with economics. Everything is economics driven, so the cost of energy incentivizes, alternative, heating approaches for district heating. I mean, district heating is low heat requirements. I mean, we're not trying to heat up something to 1000 C to calcine, cement or whatever. So I would assume cost of energy is a factor, and population density is also a factor, that you can install infrastructure and it can, affect a larger population. Just speculations on my end.
Yeah, that meshes with what I heard, especially population density, and then of course historic. When did countries start to invest in that? In the case of Germany, it was really early. But it's not just in Germany. I think Philadelphia has systems. They're often not very visible, and so people don't even know they exist. As a matter of fact, few people here might know that a similar system existed until maybe a decade ago, where the Coors Brewery supplied power to the Mainz campus in a very similar fashion. But then they did fuel switching, and it didn't. They went from coal to gas, and it didn't make sense anymore.
And I would say it's not something that is not pursued in the United States. What comes to mind is a project in Minneapolis, St. Paul, where they're decarbonizing a combined heat and power facility to run off of hydrogen or a hydrogen natural gas mix that will provide heat and power to Minneapolis, St. Paul proper. So similar to what you're saying, Martin, of like this is happening within cities right under our noses, and we might not even realize it. There are activities happening in major cities in the United States, like Minneapolis, St. Paul.
Yes, I got lucky and had the opportunity to attend the district heating conference in Aalborg, Denmark in 2018. And all the district heating stuff was fabulous. And we stayed in a nice little flat I'd say about 4 miles from town that had mysterious heat sources that must have been underground. And it was very comfortable. And the town was very proud of their burning their trash, and their emissions from their trash was only 5%. They captured 95%. And their big thing was irritation with this giant behemoth across the fjord, which was a cement plant making all the cement for Northern Europe. And they were trying to figure out how to get a hold of that. And at the time, the cement companies were not very amenable to letting them wrap heat exchangers around their smokestacks and try and capture some of that heat. But I think watching the Europeans is going to be a fun thing. They have a lot of great ideas. I saw some huge heat pumps, huge.
The cement is interesting. I'll just add one comment about that, because you have to think about decarbonizing cement is challenging because you have purchasers, procurement officers, even within the federal government, that are adverse to cement that is different in its quality. What happens if my building collapses? What happens if my bridge collapses? And you really need to do your due diligence to demonstrate to them that, well, we got the same, compressive strength and the same material properties. Everything's going to be okay. But there's a confidence aspect from a purchaser, from the consumer, that you need to overcome, whether that's cement or other things.
Thank you. Thank you so much for your presentation. Absolutely excellent. really enjoyed it. And your comments about the developing countries kind of really resonated with me. I've been doing international development for over 20 years and attended the last 4 conference of parties, et cetera. So anyway, the work you're doing, I think, has great applications for developing countries to make sure they don't make a lot of the same mistakes that we made. But I wonder if you could expand a little bit, sorry, on annual cycle storage. In the late 70s, early 80s, I spent about 3 years doing work with Argonne National Labs on annual cycle storage, primarily for building applications, and heat pumps, water storage, heating up in the summer, using in the winter, and back and forth. If you could expand on that a little bit. Thank you.
Yeah. So one of the things that is an advantage of latent heat thermal energy storage is that phase change, right? That you store heat in the form of the change in phase from a solid to a liquid, for example. So NREL has an emerging buildings technology program. I was associated with it when I was at NREL years ago, and latent heat thermal energy storage is a way to do seasonal storage, right? Because you can set the conditions of when that phase transition happens. It can be liquid in the summer and solid in the winter, and you can store energy that way. And they're doing quite a bit of work trying to integrate technology into the building envelope, so that you don't have some big honking piece of equipment outside of your home, but it's built into the facade. It's built into the, drywall, for lack of a better term, in your home. That this technology is in there that can provide seasonal storage. That's an application that I'm aware of, at least.
I'm going to throw a little more appropriate thing at you this time.
Okay.
You went to Indiana University.
I did. Go Hoosiers.
Yeah, go Hoosiers. And I could sing the fight song
Good.
with you.
Excellent.
But when I went to grade school and high school, I explored the district heating, which was used on the Indiana University campus. So where you went to undergraduate, it was district heated. At the corner of Fee Lane and 10th was where there's a big coal pile and a big plant.
Yeah.
And there were 3 foot wide by 5 foot high concrete tunnels to every building on campus that had steam pipes going through.
Oh, wow.
And this is where all us local kids that were professors' kids, we got into those, and we went all around the campus in all of that.
There you go.
And then into Swain Hall and into the chemistry building.
I like it.
And so you were heated by district heat.
Very good. Very good.
Well, with that, let's thank our speaker. Thank you.